Welcome back to the Neural Intel Deep Dive, where we strip away the marketing hype and jump straight into the technical architecture and core implications of the latest advancements in large language models. To stay updated on the cutting edge of AI and machine learning, make sure you visit our webpage, neuralintel.org, and check out our content on YouTube.
Our mission today is highly specific. We are diving into Medmarks v0.1. This is a crucial new development that establishes the largest, completely open-source automated evaluation suite for assessing medical capabilities in LLMs.
And we're sticking to the technical details here, right? We're looking at the Sophont blog release.
Exactly. We're focused on what this benchmark measures, how it measures it, and, most importantly, what the performance data tells us about where these models are heading.
That's right. The Sophont blog release covers a massive evaluation. We're talking 20 distinct benchmarks, 46 different models, 56 configurations. It's really designed to be the new open baseline for medical AI development, and it's here because the old systems had some pretty significant technical shortcomings.
And while the headlines might say the top performers are GPT 5.1, GPT 5.2, and Qwen 3 235B.
The usual suspects.
The usual suspects, yes.
Yeah.
But the truly valuable technical insights are found not in who won, but in the quantified difficulty, the efficiency gaps, the failure modes. This deep dive is all about the engineering trade-offs that this data has now brought to light.
Okay, so let's unpack that immediately. Whenever a significant new benchmark suite like Medmarks v0.1 drops, the first, most critical question we have to ask as engineers is, why? Why did we need this? We had MultiMedQA, we had MedHelm, HealthBench. Why was building this an absolute technical necessity?
It was a necessary response to three distinct technical failures.
Yes.
Saturation, reproducibility limitations, and scope restriction.
Yeah.
Let's start with MultiMedQA. It has been a foundational standard for a while.
Right. It's the one everyone quotes.
It is. But its core technical failing is that it focuses overwhelmingly on knowledge recall. These are tasks structured like digital medical licensing exams.
So it's testing the model's ability to just pull out a fact, like a definition or a standard treatment, not actually apply that knowledge.
Precisely. And because of the just explosive advancement in LLMs over the last couple of years, the frontier models are already way too good at these simple recall tasks. The benchmark became statistically saturated.
Saturated, meaning what exactly?
When the best models are scoring 95% or higher, the benchmark just loses its ability to differentiate. It can't tell you the difference between an excellent model and a truly superior one.
And it doesn't give you a signal for where to do research next.
Exactly. It no longer tells you where the architectural headroom still exists. We need tasks that measure reasoning, synthesis, safe application, not just a glorified lookup table.
So MultiMedQA basically became a victim of the success of the very models it was designed to measure. It's like testing a Formula One car on a suburban street. You can't tell which is faster because the road is the limiting factor.
That's a perfect analogy.
Yeah.
The limiting factor was the test itself. So next you have MedHelm from the Stanford team. This suite, to its credit, attempted to be broader, more reflective of real-world use cases. A step in the right direction.
Sure.
But it suffered from a critical and, frankly, a self-inflicted technical limitation, one that just destroyed its utility for the broader open-source community.
Okay, what was the technical bottleneck there? What stopped it from becoming the standard?
Only 13 of its 35 data sets are publicly accessible.
Oh.
Yeah, that's a massive fundamental issue for reproducibility. If you as a researcher can't access the full evaluation data, you can't replicate the results.
And you can't extend their leaderboard with your own model without going back to them?
Exactly. It centralizes everything. It makes MedHelm a black box evaluation for most of the industry.
Which just completely undermines the principle of open, verifiable science. That's the cornerstone of AI research.
Precisely. Openness isn't just a philosophy. It's a technical requirement for a robust benchmark. If you can't see the data, you can't fully trust the claims.
So we have saturation with one and reproducibility problems with another. What was the third gap?
The third gap was HealthBench, a more recent suite. Valuable, but its technical scope was just too narrow.
How so?
HealthBench focuses solely on evaluating medical conversations.
Okay, so it measures how well a model can talk to a patient, explain something clearly, maybe show empathy in a chatbot. That sounds useful for some things.
It is useful, but the medical domain is so much more than polite conversation. Think about the actual tasks. You have complex administrative workflows, you need precise logical reasoning for diagnoses, you have to interact with structured electronic health records, and critically, you have to perform specialized medical calculations, unit conversions, dose tracking.
All of which HealthBench just ignores.
It completely neglects those non-conversational operational capabilities.
And that's dangerous. You could think your model is ready for a clinic because it talks well, but it might fail a catastrophic calculation.
That's the risk. So Medmarks v0.1 is the technical response to all three of those gaps. It's engineered from the ground up to be completely open source, easy to run, and it's evaluated on this massive, clinically relevant taxonomy. It has the full spectrum: recall, information extraction, reasoning, EHR tasks, and those medical calculations everyone else missed.
And by being open, it solves the MedHelm problem. And by being broad, it solves the saturation and narrow scope problems of the others.
Exactly. It's the new baseline.
Now that we understand the motivation, let's drill into the nuts and bolts of the Medmarks architecture. The 20 benchmarks are split into two subsets. Tell us about that division.
So the primary division is based on the solvability of the answer. First, you have Medmarks verifiable. This is 14 of the benchmarks. These are tasks with objective, exact answers.
Right or wrong? Binary.
Binary. Think multiple choice questions, or, and this is the key one, the MedCalc bench, where the answer is a specific number. These are the ones where you can have automated deterministic grading.
And the second group, which I imagine is much harder to grade, is Medmarks OE open-ended.
Correct. Medmarks OE has 6 benchmarks where there is no single objective exact answer. These are tasks like evaluating advice to a patient or synthesizing conflicting clinical notes. The output is generative, it's nuanced, and it requires external judgment.
Which brings us to the core innovation here, the primary ranking metric they use: the weighted mean win rate. This sounds more complex than just accuracy. How does it work, and why is it necessary?
It's necessary because a simple average accuracy can be really misleading. The mean win rate itself is calculated as the average proportion of models that a given model outperforms across all the benchmarks.
So if my model beats 30 out of 45 other models on average,
its mean win rate is 30 divided by 45. It's a peer relative metric. It tells you how well your model performs relative to the entire field being tested.
Okay, so it's a ranking based on head-to-head performance, but then there's the weighted part. Explain the technical function of that weighting factor.
This is the genius part. To make that rate weighted, they applied a normalization factor. Each benchmark score is weighted by the logarithm of the dataset length.
Okay, the logarithm. Why the log function specifically? Why not just use the raw number of questions in the dataset?
If you used the raw length, a single massive dataset, let's say one with 500,000 sample facts, would just numerically overwhelm a smaller but much harder expert-level dataset. Your total score would just be a reflection of how well you did on the easiest, biggest benchmark.
I see. The log function kind of compresses that scale.
It acts as a statistical compression technique. A dataset that's 10 times larger gets a higher weight, yes, but crucially, it does not get 10 times the influence. This ensures that those smaller, harder, high-signal datasets still have a meaningful impact on the final score. It makes sure the benchmark is testing a breadth of capability, not just mastery of abundant, easy data.
That clarifies the engineering trade-off perfectly. You're trading raw statistical power for balanced representation across a diverse set of clinical challenges.
Exactly. Without that log weighting, the leaderboards would just tell you which models are best at the most common tasks, not which are the most clinically useful.
Now let's turn to the open-ended tasks. Since they're subjective, you have to rely on an LLM as a judge system. But we've seen this before. What specific technical rigor did the Medmarks team use to make sure their judge was reliable?
This is a major area of advancement. Historically, open-ended grading relied on classical metrics like RUJL or N-gram overlap.
And those just look for word overlap. They can't capture semantic meaning. A model could use a perfect synonym and be marked wrong.
Precisely. They lack world knowledge. So the Medmarks team decided to use a frontier model as the judge. But the selection was far from arbitrary. They followed a really rigorous 3-step technical validation process.
Okay, walk us through that process.
Step 1 was infrastructure. They sampled a large subset of the open-ended questions and ran them through various potential LLM judges, caching all the answers. This gave them a baseline for inter-judge agreement. Step 2 was the crucial part. They built a custom web app for human experts to do blind, head-to-head comparisons. But here's the clever bit. They focused the human effort specifically on the questions where the LLM judges disagreed the most.
That's smart. So you're not grading the models with humans, you're grading the judges with humans, and only where you need to break a tie.
Exactly. And the third step was a consistency check. They preferred judges that scored well with the humans and showed low variance across the initial rollouts. High consistency suggests reliability.
So which models made the cut?
The primary judge for most of the open-ended benchmarks was GPT-5 Mini. Interestingly, for one really complex task, med-case reasoning, the human graders actually preferred GPT-5 Nano. This whole process shows they were aiming for objective measurement, even in a subjective domain. It's a technical upgrade over just counting words.
This brings us to the neural signal check. Here's why this development actually matters at a technical level. We've talked methodology, now let's talk findings. Let's look at the raw performance data, the difficulty gradient, and what it all implies.
When you map the performance across the verifiable benchmarks, a really clear difficulty gradient emerges. This is basically a roadmap for future research. You can see the easy, moderate, and hard tasks.
Okay, so where did the current models do best? What are the solved problems?
The easiest tasks, by far, were the long health tasks. Performance there is high, often over 80% for the best models.
Why is that?
Because these benchmarks are primarily testing long context handling. The data suggests that context window management, which used to be a huge hurdle, is now a relatively solved problem in the latest models.
What about the moderate difficulty zone, the middle tier where performance starts to drop off?
That's the most competitive area. You have benchmarks like MARC, MedQA, and really importantly, MedCalc-Bench.
Let's do a deep dive there. MedCalc-Bench. That sounds like it should be easy for an LLM. Why is it only moderately difficult?
This is where a critical implementation detail comes in. The overall performance on this benchmark is strikingly low, averaging only around 43%.
That feels counterintuitive.
Yeah.
These models have seen countless equations. Why would they struggle with medical calculations?
Because the sources explicitly state that the LLMs were not provided calculator use for this benchmark.
Oh.
It's a technical setup choice with massive implications. The low score doesn't mean they don't know the right formula. It means they have a fundamental weakness in their pure, innate, internal reasoning core for arithmetic.
So MedCalc-Bench isn't really a test of medical knowledge here. It's an isolated test of the model's raw math ability, which without a tool is weak.
Exactly. It's a proxy for their pure arithmetic competence. It provides a strong signal that future architectures need either vastly improved internal numerical processing or, more likely, mandatory standardized tool integration.
That is a fundamental challenge for trustworthy deployment.
Okay, let's go to the other extreme. The hardest tasks. Where is the real headroom for improvement?
The benchmark that truly stumps the current models is MedXpertQA. Scores here are hovering around 30%, even for the biggest models.
And what does that test?
It demands expert-level clinical reasoning, diagnosing complex cases, distinguishing subtle symptoms, combining multiple knowledge streams. It's just we have a long way to go to get from good test takers to true expert clinical aides. On the open-ended side, med-case reasoning and parts of HealthBench were also extremely difficult.
So the data is clear. We're still far from achieving true expert-level competence.
That's the hard truth. Now let's look at scaling laws. The old rule is bigger is better. Does that hold up in the medical domain?
Well, when you categorize them by size, tiny, small, medium, large, and API, you'd expect a pretty clear upward trend.
And generally, you see that. On easier tasks like long health, the large models are scoring close to 90%, while the tiny ones are down in the 50s and 60s. More parameters clearly helps. But the interesting data always comes from the exceptions. What happens on those really hard tasks?
On MedXpertQA, the scaling law starts to break down. The performance gap between model sizes narrows significantly. The large models are clustering around 30% accuracy, but the tiny models are around 15%. That's only a 15-point gap, much smaller than what you see on easier tasks.
Why does that happen? What does it imply?
It suggests a profound limitation. For these extremely difficult reasoning tasks, just adding more parameters is giving you diminishing returns. The task complexity has exceeded the fundamental reasoning capacity of even the largest current transformer architectures.
So brute force is failing. We need a new architectural or training approach to crack that MedXpertQA ceiling.
Exactly. We're not just waiting for GPT-6 to be bigger, we're waiting for it to be fundamentally smarter.
Speaking of smarter architectures, let's talk about the overperformers. Which models defied the scaling trend?
The Qwen3 reasoning models. They consistently punched above their weight class. For example, the Qwen3 4B thinking model, which is tiny, actually outperformed the mean win rate of the entire small size class.
That's powerful evidence that efficient architecture can trump brute force size.
Absolutely. And conversely, you have the underperformers. Models like Hermes 470B, a large model, performed worse than the average medium model.
Which is a clear signal that architectural or training inefficiencies can completely negate the benefit of a large parameter count. Size isn't everything.
It gives you capacity, but sophisticated training dictates what you can actually do with it.
Building on that point, let's move into optimization. How did Medmarks quantify the gains from domain adaptation from focusing a model specifically on medicine?
They gave us a really clean, controlled experiment with the GEMMA models versus their medically tuned counterparts, MedGemma.
Same base architecture, just with different fine-tuning.
Exactly. It isolates the effect of the domain-specific post-training. And the results were clear. Both the MedGemma 4B and the 27B models showed a significant and consistent boost in mean win rate over their generalist-based models.
Well, much of a boost.
The 4B model jumped by nearly 4 percentage points, and the 27B jumped by over 5. And more importantly, the sources call this a Pareto improvement.
Meaning it got better on almost every single task without getting worse on any?
That's right. It's undeniable, quantitative proof that adapting foundation models to the medical domain provides reliable gains across the board.
But if we look at the overall leaderboard, the top-tier generalist models like Quinn 3 and the GPT-5 models still beat these specialized MedGemma models. What does that imply?
It implies a two-step path. Step 1, build the best possible general-purpose foundation model, maximize its underlying reasoning capacity. Step 2, apply targeted medical post-training to that foundation. The ceiling is set by the base model's intelligence, not the domain tuning.
Let's shift our focus to cost. Performance is useless if it's too expensive to run. What did Medmarks reveal about the massive efficiency gap between proprietary and open-weight models?
This might be the most economically impactful finding in the whole study. The data shows a dramatic split in token efficiency.
So who's on the efficient frontier?
The Pareto frontier for accuracy combined with low cost is dominated by models like GPT 5.1, GPT 5.2, and Claude Sonnet 4.5. They achieve high accuracy, over 70%, while using remarkably few tokens, typically less than 700 per response. They're accurate and they're cheap to run.
Now contrast that with the big open-weight models. What's the scale of the inefficiency there?
The largest open-weight models like Quinn 3 235B, which can match the proprietary models on accuracy, demand 5 to 6 times the token volume to do it.
5 to 6 times.
Yes, we're talking 300 to 500 tokens or more per response compared to under 700.
That's the difference between running a query for $1 versus $5 or $6. That's a massive operational bottleneck for any hospital trying to deploy this at scale.
It is. It shows that while open models have caught up on accuracy, they haven't solved the high computational cost of running that complex internal reasoning process, that chain of thought. The frontier labs have clearly found a way to compress that reasoning trace cheaply. That's the next big hurdle for the open community.
Let's talk about that reasoning process itself.
Yeah.
What happens when you post-train a model specifically to think before it answers?
So reasoning post-training, turning a standard Instruct model into a thinking model, generally provides a clear performance boost. You see this consistently with Olmo and Quinn 3. That internal thought process allows for self-correction and more structured problem-solving, which leads to a quantifiable improvement.
But there's always an anomaly. Tell us about the Minstrel anomaly.
Right. The Minstrel family of reasoning models, when compared to their standard instruction-tuned versions, consistently underperformed across almost all the Medmarks datasets.
Which is the exact opposite of what you'd expect, so what went wrong?
The sources suggest a few possibilities. One is catastrophic forgetting, where the reasoning training overwrites useful general knowledge. Another is overfitting to the specific reasoning data they used.
Or maybe the reasoning data itself was just not well aligned with the instruction data.
That's the third possibility. The Minstrel anomaly is a crucial cautionary tale. Just adding a reasoning step isn't a silver bullet. The engineering and data curation have to be perfect.
Let's shift to how these models actually fail. Medmarks tested what they called the overthinking phenomenon. What did the data show about token use when a model gets an answer wrong?
This is a really interesting technical observation. Across multiple models, they found a clear pattern. Models consistently generate more reasoning tokens for questions they ultimately answer incorrectly.
That seems like a paradox. Why would more thinking lead to a wrong answer? Does the model just confuse itself?
The interpretation they offer is slightly counterintuitive. It's not that the increased thinking caused the error. Instead, it suggests that when a model faces a problem, It fundamentally lacks the knowledge to solve. It exerts maximum effort. It spends its entire token budget trying and failing to find a solution.
So it's not, I thought too much and got it wrong. It's, I got it wrong because the problem was hard, and the difficulty made me try as hard as I possibly could.
Exactly. It's an expensive failure mode, which feeds right back into that efficiency gap we talked about.
But they ran a controlled test to see if more effort is actually beneficial
Right.
using the GPTOS models.
Right. And that control test is crucial. With the GPTOS models, you can explicitly set the reasoning budget to low, medium, or high.
And when they cranked up the budget,
Performance went up. The results were definitive. Increasing the reasoning budget from medium to high on both the 20 billion and 120 billion parameter models produced stronger results overall.
so more effort is generally good, even if the models waste tokens when they fail on the hardest problems.
Correct. The overall benefit outweighs the cost of those expensive failures.
Let's move on to model precision. We need to talk about quantization. How does reducing a model's precision impact its medical performance?
Quantization is, just reducing the precision of the model's weights to save memory and increase speed. It's a key trade-off for deployment.
But you risk degrading the accuracy.
That's the risk. So they tested the Quinn 330B model across full precision 8-bit and the really aggressive 4-bit precision.
And what was the performance trade-off?
The finding is a huge validation for modern deployment techniques. They found minimal, almost zero performance degradation all the way down to 8-bit quantization. Only the highly aggressive 4-bit scheme suffered a small but consistent penalty.
That is a major technical win. It means you can confidently quantize these medium-sized models to 8-bit, preserving clinical performance while making them way faster and cheaper to run on smaller GPUs.
Absolutely. Quantization is production ready for this. Finally, let's talk about a more subtle vulnerability: order bias. Positional bias and multiple choice questions.
The idea that a model might just favor option A, or the shortest answer, regardless of the content. Does this still exist in the latest models?
It absolutely does. They tested this by running 3 rollouts with randomized answer orders. And they confirmed that modern models, even frontier ones like Grok 4, are still susceptible.
And Grok 4 was a standout example of this, wasn't it?
It was noted for its high variance. When they truffled the answers, its score fluctuated wildly. Then, as a check, they fixed the answer order for all 3 rollouts, and the variance dropped dramatically.
So the variance was almost entirely due to the answer shuffling, proving a strong positional bias.
Yes. And the MedBullets benchmark had another interesting test. They added an extra distractor answer, going from 4 to 5 options.
What did that reveal?
It tests the model's confidence. If you're really certain a 5th wrong option shouldn't throw you off. But the data showed that adding that distractor, especially combined with shuffling, caused a large drop in performance. And this effect was much greater for the smaller models.
Because smaller models have less capacity and are less confident in their knowledge, so they're more easily distracted by noise.
Exactly. It confirms a hierarchy of robustness that's directly tied to model size.
This is where Medmarks pivots from just being an evaluation tool to a driver for future development. It's built on Prime Intellect's verifiers library. What's the technical implication of that choice?
It's profound. By using the verifiers library, the underlying data sets can be easily used as ready-made reinforcement learning environments. It transforms Medmarks from a ruler into a gem. It's not just for measuring models, it's for training them.
So researchers can immediately use these data sets as a feedback loop to improve their model.
Exactly. The framework provides train-to splits that fit right into established RL frameworks like PrimeRL and SkyRL. It accelerates the path toward creating better models that are optimized specifically for these clinical tasks.
Now let's get into the deep mechanics of that. The custom multiple choice grading function. Why do they need something so complex instead of just checking for an A, B, or C?
Because when you're building an RL environment, you have to be robust to messy outputs. Smaller or less tuned models often ignore formatting instructions. They might output the letter, or the text of the answer, or both, or a bunch of extra thinking traces.
And a simple string match would mark all of those as wrong, even if the model got the substance right.
Precisely. The custom function normalizes the output, strips out junk, handles capitalization, and then uses complex logic to check for all the different ways a model might correctly answer.
But this complexity creates a new technical challenge, right? Reward hacking.
It does. The sources anticipate this. The major problem they note is the edge case where a model outputs the wrong letter, followed by the correct text. Currently, that's graded as incorrect.
I see. An RL agent doesn't care about clinical truth. It only cares about maximizing its score, so it could learn to game that specific grading logic.
That's the exact challenge. It might learn to format its answer in a way that tricks the grader, even if its underlying reasoning is flawed. It's a classic problem in designing stable RL environments.
Looking forward, what new benchmarks are they planning to add?
The roadmap shows a clear shift toward more complex agentic tasks. They plan to include things like ACI Bench, MedAgent Bench, Agent Clinic.
The names say it all. It's about evaluating models as multi-step clinical agents.
Exactly, moving from a knowledge base to an actionable decision support agent.
And they also acknowledge the big limitation right now is that it's all text.
Yes, they explicitly state that medicine is inherently multimodal. You have imaging, lab results, visual data, so the future plan is to expand into vision language and other multimodal capabilities.
Which is where that MedXpertQA ceiling will really start to lift. Fusing medical imagery with text, that's the next frontier.
To summarize the technical landscape Medmarks has revealed, we now have the essential open-source baseline the community desperately needed. It's both a scoreboard and a development environment.
Right. We've quantified the benefits of domain adaptation with the MedGemma Pareto improvement, and we've verified that 8-bit quantization is deployment-ready, which is huge for operational cost. And crucially, we've pinpointed the high technical challenge of expert reasoning with MedXpertQA, a problem that just scaling up parameters is failing to solve.
And we have the hard evidence of that massive efficiency gap. The proprietary models are 5 to 6 times more token efficient at reasoning than the best open source alternatives. That cost disparity is now the next critical target for innovation.
So here's the final provocative thought for you to mull over. The data clearly shows that models use the most tokens on problems they get wrong, that expensive overthinking on failure. What if future research can develop a reliable meta-reasoning layer? An architectural control system that can recognize when the model's internal monologue is fruitless, when it knows it lacks the knowledge, and just stops the generation early.
If you could build that, would that optimization not only yield massive cost savings by avoiding wasted tokens, but also fundamentally change the efficiency ratio for open source models? Could the open community close that 5 to 6 times gap just by being smarter about when to give up? It's a fascinating question of introspective control that Medmarks now lets us start to answer.
A question driven entirely by the data. For more technical deep dives into the latest in AI and ML, visit neuralintel.org or check us out on YouTube. We'll see you next time.